Hello, everyone. Welcome to the ILTA Physics online problem-solving lecture. Today, we're going to work on some problems regarding friction. Friction is a force that opposes the change in motion of an object. As you can see in the picture, when someone pushes a large wooden crate, the friction force acts in the exact opposite direction of that pushing force. In the end, the object moves based on the remaining force after subtracting friction from the push. This is why people often compare friction to the laws of nature, saying there's no such thing as a free lunch. The problems we'll solve today are about static friction and kinetic friction. Specifically, these types of problems require us to analyze the accelerated motion of an object while taking friction into account. First, let's quickly summarize the basics of friction. Friction is mainly divided into static friction and kinetic friction. Static friction is the force that resists an object from sliding. It always acts in the opposite direction of the motion and parallel to the surface. What's interesting is that the magnitude of static friction perfectly balances out the force applied to the object. If we push an object but it doesn't move, the static friction at that moment is equal to our pushing force. However, there's a limit to this, which we call the maximum static friction. We calculate this by multiplying the coefficient of static friction by the normal force. Next, kinetic friction is the force acting when an object is sliding across a surface. It also acts in the opposite direction of motion, but unlike static friction, it isn't always equal to the applied force. Kinetic friction is proportional to the normal force and is determined by a constant value found by multiplying the coefficient of kinetic friction by the normal force. Therefore, if we push an object with a force greater than the kinetic friction, the object accelerates and slides by the amount of that difference. A cool fact is that kinetic friction doesn't depend on the speed of movement. It only depends on the normal force. Also, since kinetic friction is usually smaller than static friction, it takes less force to keep an object moving than it does to get it started from a stop. Now let's solve some basic types of friction problems together. Problem number 27 is a basic type regarding kinetic friction. Two workers are moving a 300-kilogram crate. One is pushing from behind with a force of 386 newtons, and the other is pulling from the front with a force of 350 newtons. If the crate is moving at a constant speed, the question asks for the coefficient of kinetic friction. The key to this problem is that even though forces are being applied, the crate is in constant velocity motion. If we analyze this physically, we can summarize it like this. From a kinematical perspective, constant velocity means there is no change in velocity at all. Therefore, the acceleration of this object is zero. Additionally, looking at this constant velocity state from a kinetical perspective, it means one of two force conditions is met. The first is when there are no external forces acting at all. In this case, Newton's first law, the law of inertia, applies. Without external interference, a moving object will keep moving at its original speed due to its inertia. The second case is when the net force, or the sum of all forces acting on the object, is zero. Even if multiple external forces are hitting the object, they cancel each other out, resulting in a state of zero. In physics, we call this dynamic equilibrium. Most physics problems are designed for us to analyze motion using this dynamic equilibrium situation. In other words, the clue moving at a constant velocity allows us to set up the equation, the sum of all applied forces equals zero, to solve the problem. In this problem, the forces applied by the two workers are exactly canceled out by the kinetic friction, so the box moves at a constant velocity. All right, let's draw a free body diagram for this motion. We'll set up a coordinate system and assume the crate is moving to the right. Let's think about all the forces acting on the crate. The weight of the crate acts downward, and a normal force of the same magnitude acts upward. To the right, we have the forces F1 and F2 applied by the two workers. While it's not strictly necessary for the free body diagram, we've noted that the crate moves at a constant velocity to the right. Since the net force on the crate must be zero, a kinetic friction force acts to the left with a magnitude equal to the sum of the two pushing forces. The sum of the forces from the two workers is 380 newtons plus 350 newtons, which equals 730 newtons. Kinetic friction is calculated by multiplying the coefficient of kinetic friction by the normal force, and the normal force is equal to the downward weight of the object. If we plug the mass of 300 kilograms and the acceleration due to gravity, 9.8, into the equation, we get the following. The coefficient of kinetic friction for the wooden crate comes out to 0.248. Since the coefficient of friction is a ratio of two forces, it has no units. In this problem, the most important thing was to accurately understand what it means for an object to move at a constant velocity despite forces being applied. Problem number 29 is a type that combines friction with accelerated motion. A 1,000 kilogram car is driving at 40 kilometers per hour on a wet road with a coefficient of kinetic friction of 0.6. When the driver hits the brakes, we need to find the distance it takes to come to a complete stop. The first part of the problem describes kinetic friction kinetically, and the second part asks about displacement or distance in accelerated motion. This is a great problem because you need to connect these two concepts using frictional acceleration. After reading the problem, you should be able to visualize a kinematic diagram like the one on the right. The car is moving right at an initial velocity of 40 kilometers per hour. Then the brakes are applied, and it stops at a final velocity of 0. We need to find the displacement d during this deceleration. It's important to note here that the acceleration causing this change in velocity acts in the direction of slowing down, meaning to the left, opposite to the motion. Now, let's draw a free body diagram for this. Let's show all the forces acting on the object at some point during the deceleration. The weight acts downward proportional to the mass of the car. The normal force acts upward with the same magnitude. And once the brakes are applied, the kinetic friction between the car and the road acts to the left. First, kinetic friction can be calculated as the product of the coefficient of kinetic friction and the normal force, where the normal force equals the downward weight. If we simplify this, kinetic friction can be expressed as mass times the quantity of the coefficient of kinetic friction times the acceleration due to gravity. Therefore, the frictional acceleration caused by kinetic friction is 0.6 times 9.8, which equals 5.88 meters per second squared. Please be careful. As seen in the motion diagram and the free body diagram, the direction of acceleration and friction is to the left. So, in our equations, we should plug this in as a negative value. Now, let's calculate the displacement of the object produced by this acceleration. Using the relationship between velocity and displacement for accelerated motion that we learned earlier, and since the final velocity is 0, we can rearrange the formula for displacement like this. In this case, the acceleration used is the frictional acceleration acting to the left. So if we substitute the value for negative sub f, the result is calculated as 136 meters. This problem connects the kinetical concept of friction to find acceleration, and then uses that acceleration in a kinematical process to calculate travel distance. Please review this so you can accurately understand the relationship between friction and accelerated motion. That's it for today's lecture. You all did a great job. I'll see you next time.